Okay, welcome back. Today what we are going to talk about is the notion of visualizing functions. So recall last time we have talked about the usual definition of functions or the usual context in which functions appear as functions from the set of real numbers to the set of real numbers. So here is our usual mental picture of a function. It has domain to be the real numbers and codomain also to be the real numbers, and such a function is best represented as a graph. So we talked about what the graph meant and also what continuity meant last time. So for each value of x you look at the corresponding point xf of x on the graph and you sort of let x vary, and what you get, what it traces out is what we call the graph. And what really is meant by visualizing functions, what I would like to mean by it is how do you do something similar for functions which are not defined on R to R, for instance, but rather say functions which are defined on the plane, which is what we usually denote as R2. So let us do various examples. So what I really want to do in this lecture is to consider a few examples of functions. But not from R to R. So let us do the first one. It is a function from R to R2. Okay. So R of course is just the real line, and so this function maps each point in this real line to a point on the plane. Okay. So the plane is what we usually denote R2. Now the question is, how do you really try and form a mental picture of this function, or how do you draw a picture which gives you some idea of how the function behaves and so on. So the obvious thing to do is to sort of try copying something like what we did for graphs, which is to trace out all the points that you get. Okay. Now but it is slightly different. So here is what we would try and do maybe to get an idea of what this function does. Think of this domain as being like time. Okay. So instead of calling it as x as is conventional, let us call it t for now to remind ourselves that it is like time, and think of this function as doing the following. For each value of time it gives you a certain position on the plane. Okay. So this is the x axis and the y axis, and you should really think of this function as describing the motion of a particle on the plane as time varies from say -infinity to infinity, or maybe only on some interval, say time going from say 0 to 1 and so on. So the motion of the particle, if you want to really describe it, here is what you would want to say. Take time 0 and sort of see where the particle is. It is say at some point on the plane, and as you increase the value of t, you look at what f of t is. So f of t would trace out some curve. So as time increases, the position of the particle varies and it becomes maybe something like this. It could trace out some strange curve. This is what happens as time increases. But of course here we also have t negative. T can also be all the way to -infinity. So maybe it traces out some curve like that when time comes from -infinity to 0. So this is the position at time t equal to 0. So these are the positions that it traces out when the time is positive, and these are the positions where the particle was when time t is negative. Okay. So you should really think of this function, a good visualization or a good mental picture to form of this function is in terms of the curve that it traces out on the plane. Okay. So the curve of course also comes with a direction. It tells you which is the direction in which you move as t increases. So let us do an example. So let us take the function f defined as follows. F of t is, so if you want to write formulas for functions from R to R2, what would you want to do? For each value of t you must specify a point on R2, okay, and a point on R2 is actually two coordinates x and y. So here is what you would say, let f of t be some function of t. So what I should write here should be a function of t, it varies as t varies, and here I should write another function of t. Okay. So this is sort of the most general way of writing a function which goes from R to R2, which is, you should say it's essentially f of t equals the pair x of t comma y of t, where x of t and y of t are just functions from R to R. So where, so I'm not yet at my example, so let me just say note a function f from R to R2 is really always of this form x of t y of t, where what are x of t and y of t? We should think of x as being a function from R to R. For each value of time t, it gives you a single real number, the x coordinate, and y is now a function from R to R again. For each value of time t, it gives you some y coordinate. Okay. Now let us take an example with actual functions. So suppose I take f of t equals t square minus 1, that is the x coordinate. Y coordinate is t cubed minus t. Okay. So here is your function f, and so what we want to do is really figure out what is the curve that is traced out by this function as time t changes. So let us do the following. Let us look at where this particle is when t equals 0. So if you plug in t equal to 0, you get minus 1 comma 0. So this point here on the x axis, minus 1 comma 0, this is the position of the particle at time t equal to 0. Okay. So let us just denote that this is position at t equal to 0, and then we see what happens as time increases. T becomes say 0 or well greater than 0, or in fact as time decreases, whatever you do to time, either increasing or decreasing, observe that t squared will always be positive. So here are various points to note about. So let us see what all we can deduce. T square is always greater than or equal to 0 no matter what t is, positive or negative. In other words, t square minus 1 is at least minus 1, okay, for all values of t, for all t in real numbers. So this of course means that this particle behaves in the following manner: the x coordinate is always minus 1 or higher. Okay, it is always to the right of this point minus 1 0 if you wish. Okay, so that is something to keep in mind. Now what happens as you increase t, for instance? So let us figure out if t goes from 0 to 1. So as long as t is smaller than 1, the x coordinate is still negative. So let us analyze what happens when t is between 0 and 1. T square minus 1 is greater than or equal to minus 1, less than or equal to 0. So the x coordinate varies between minus 1 and 0, and it in fact reaches the value 0 correctly at t equals 1. Okay. So let us also figure out what happens at t equals 1. So let us call it f of t equals 1 is, if you plug in t equals 1 into the formula, well, t square minus 1 and t cube minus t are both zeros. Okay. So f of 1 is in fact 0 0, which means at t equals 1 it is at the origin. Okay. So this happens for and how does that happen? As t goes from 0 to 1, the x coordinate increases from minus 1 all the way to 0. Okay. And the y coordinate is in fact, what do we know about the y coordinate in this range? So if I take t from 0 to 1, let us look at the y coordinate. It is t cube minus t, which is, well, it is t times t square minus 1. So in fact this is negative, because t square minus 1, as we just said, it is the x coordinate is negative, and you are multiplying it by a positive quantity which is t. So t cube minus t is negative when t goes from 0 to 1. So here is really the question. So let us just remove this. This is where the particle is at t equals 0. This is where it is at t equals 1. That is the origin. Now the question is, how did it go from here to there, right? We are trying to get an idea of what the shape of the curve is. So when t changes from 0 to 1, the x coordinate is of course negative, it continues to be negative, whereas the y coordinate is positive. So the particle sort of stays in this quadrant, it is somewhere here the entire time. Okay. So now all that remains is sort of to try and get an idea as to what the shape of the curve might be. Okay, so let us see. But maybe before we do that, here is another thing to note as well, that when t goes in the other direction, if t is say negative, okay, if t is -1, then again we will let us do the following. Let us just see what you get when t is -1. You still get 0 0, because t square -1 is a 0. Okay. So here is an additional point to keep in mind, that the particle is actually at the origin when t equals 1, also when t equals -1. Okay. So for the moment, let us say we want to analyze what the particle does between -1 and 1. Okay. So maybe I will leave this part as an exercise, just try and figure out what the shape of the curve must be, maybe just by plotting a few points and so on. So when t goes from 0 to 1, so let me just tell you what you expect to get. So if t goes from 0 to 1, here is what happens. T is it starts at 0 and goes to 1, then as we just said, the y coordinate is positive, whereas the x coordinate is between -1 and 0. Whereas if t is the other part, that is it is between -1 and 0, then here is what you get. Here is the shape of the graph or the shape of the curve when t is between, sorry, this is -1 and 0. Okay, it traces out these two things, and now here is again something that will require some more analysis of this kind. What happens if t increases further, say I go from 0 to 1, and what happens beyond that? Let us erase this. Now if you increase t beyond 1, here is what will happen, sort of do something like that. And what if t is say even smaller than -1, then it is a curve like that. Okay, it is not quite a straight line, it is some curve, but it lies in that quadrant. So this is basically when t comes from -infinity down to -1. So this is when t is less than equal to -1, and this is what happens if t is at least 1. Okay. So I haven't quite done the entire analysis, it is something that you should certainly try and do yourself. So the point of this, however, is the following: when you want to try and understand a map from R to the plane, what you should really try and view it as is as something which describes the motion of a particle, and therefore what gives you maybe a very good idea of what the function does is actually drawing the path that is traced out by the particle as it moves. Okay. Now let us do again another example. Now for function f, sort of the opposite thing, going from R2 to R, and now we want to again see what sort of picture can we draw of this function, right? What is a graphical representation? So how do we picture such a function? So let us say there are actually two different ways of understanding functions which go from R2 to R. So firstly, R2, remember, is just the plane, R is just the real line, and a function therefore does the following: it associates to each point xy on the plane, it associates some real number. So you would often want to say, if I say this function f acts on a point on the plane and gives me some real number. So the real number I get when I act the function on the point is this is probably how you should denote it if you want it to be absolutely proper, but there are too many brackets here, and we often just write this as, so note, this is probably what would constitute absolutely correct notation, but this is often written as, is simply written as a function acting on the pair x comma y. Okay. So, this is really what you would call a function of two variables, right. So, the two variables x and y you want to think of as being the x coordinate and the y coordinate. And so, I was going to say what sorts of pictures does one draw of such functions. Well, the first picture is of course just the graph itself. So, what is a graph? Well, recall what the graph meant in the case of a function from R to R. You drew on one axis you drew the domain, and on the other axis you just drew the codomain. And for each point of the domain x you mark off on the vertical side the value of the function at that point, and then you join all of these, right. So, this was the procedure for obtaining a graph if the function was a function from R to R. Now, if you want to do something from R2 to R, well, it is more or less the same idea. Instead of this, the domain is now a plane, right. So, let us think of the domain as being the xy plane, and for each point on the xy plane what you have is some function value which you now plot along the z axis. So, you have got the z axis here, and so for each point you will have something like this. So, this is vertical along the z axis. So, this point here has coordinates x and y, those are the x and the y coordinates, and the z coordinate is f of x y. Okay, and you do this for every single point x y on the plane, okay, and doing that will give you several such points, and what you do is really join all of them up, okay, and what you will typically get is some sort of surface, a two dimensional okay, so it is sort of this surface here. And that is what we call the graph of this function. Okay, so let us just get rid of the one dimensional graph. So, this is how you plot the graph of a function of two variables. So, let us see what is an example of an actual function. If I take a function f of x comma y, just be the function x squared plus y squared, then if you try and draw the graph of this function, what it does is that for each value of x and y it gives you sort of the distance squared from the origin. Okay, so, the farther the point is from the origin, the larger the value of the larger the z value essentially. So, if you sort of join all of these up, so let me just tell you what you will get. You will sort of get a surface like that. This is sometimes called a paraboloid. So, this is a paraboloid. And what is the typical point on this paraboloid? What is it going to look like? It has x y as x coordinates, y coordinates, and the z coordinate is x squared plus y squared. It is a typical point on the paraboloid. And observe that the paraboloid has the following feature, that if you take cross sections, if you cut it by a plane that is parallel to the xy plane, then what you get here is exactly a circle. So, no matter where you cut it, as long as you cut it parallel to the xy plane, you always get a cross section which is a circle. So, this is sort of the second picture that one tends to draw of functions from R2 to R. So, this is sometimes called the contour diagram or the level curves. So, this is a contour plot of a function of two variables. So, what you do is, well, you do not really need a three dimensional diagram at all. You can just do all this on the plane. Just take all values x y, well, you take the xy plane, and on this plane you plot the curves which are given by the equation f of xy equals c. So, plot the curves C, where C is every possible real constant. So, where C varies over the real numbers. Okay. So, let us look at what this would have meant in the example that we just wrote out. If I take the function f of x y equals x squared plus y squared, notice that being a sum of two squares, the value of this function is always positive or 0 or higher, and if you take pretty much any constant c, the curve f of x y equals c is just the curve. So, let us take c, it is enough to take c to be a positive constant, and the curve x squared plus y squared equals c is just a circle of radius square root of c. So, here is the circle with center the origin of radius square root of c. And if I change the value of c, so this is the radius is the square root. So, if I increase the value of c, I will get larger and larger circles, whereas if I change or rather decrease the value of c, what I get is circles of smaller and smaller radii. Okay. So, a plot like this in which you sort of also keep track of, say, what c each thing corresponds to. So, for instance, this outermost thing might have been c equals 100, and say this is c equals 50, c equals 20, and so on. It gives you some sort of mental picture of what the function is doing. Okay. So, these curves that we are drawn are sometimes called the contours or level curves. This is one level curve of f. Why is it called a level curve? It is a curve on which f takes a constant value. Okay. So, for instance, this outer circle here could have been the curve on which f takes the value 100, and the inner circle is, say, the points on which f takes the value 50 or 25 or 10 and so on. So, it gives you an idea as to where f takes certain values and how that set changes as you change the value. Okay. So, this is again extremely useful piece of information, drawing the contour plot in general. There is more stuff that one can actually deduce from the contour plot, but I will not get into that right now. Okay. So, there are in essence two different ways of understanding what the function looks like in a graphical fashion. One, you either draw the actual 3-dimensional graph, that is somewhat hard to draw in general and also hard to visualize. In this case it is easy, but an alternative would be to sort of draw the sections, the cross sections. Okay. So, the cross sections, notice, are exactly the level curves. They give you the curves that you get when you demand that f of x y has to equal some value c. Okay. So, these cross sections parallel to the xy plane, they give you, so if you plot all of them, that is what is called a contour plot or the set of all level curves. And this again has the advantage of just being a 2-dimensional plot. Okay. So, it is that much easier to handle and also contains quite a lot of information about the function. Okay. So, these are two different graphical ways. Now, sort of the final thing, since I have been playing with R and R2, the thing you would want to do is finally this. Okay. So, I have looked at functions from R to R, functions from R2 to R, from R to R2, and then finally I want to sort of slowly get into this case of looking at functions from the plane to the plane. So, what does it do for each point x comma y? It associates again a point on the plane. In other words, it associates two real numbers. Okay, so, maybe let us call it p comma q. So, I will think of this as sort of being like the p axis and the q axis. So, to each x y it associates p q. So, how do you think of or how do you visualize such functions? So, one, of course, observe what is f doing to the point x y. It is giving you an x coordinate p, or the first coordinate there, which depends on the input x y, and it is also giving you a q value which again depends on x y. Okay. So, this is probably the most general way of writing out a function from R2 to R2. To each xy it gives you a pair of functions. So, you should probably think of a map from R2 to R2 as being a package of two functions. There is the p function and the q function, and notice that the p and the q, well, what are p and q? They are just functions which do the following: to each point in R2 they only give you one real number here. So, it is just a function from R2 to R. Okay. So, each of these is just a function of a kind we have already studied, a map from R2 to R, and f is really the package of these two functions p and q. Okay. So, one way maybe of trying to understand this function f might be to understand these two functions p and q separately, and since they are functions from R2 to R, you could either draw their graph as a 3-dimensional curve or as a 3-dimensional surface, rather a 2-dimensional surface in 3 dimensions, or you could draw the contour plot of each of them and then somehow try and understand f as being made up of these two pieces. Okay. But those are all these turn out to be rather cumbersome and not so illuminating ways of understanding what this function does. Okay. And what I want to talk about next time is to think more in terms of think a little bit more geometrically about what these functions do, in terms of not just what it does to points on the plane, but maybe to what it does to say certain curves like lines or circles on the plane, what it does to regions, for instance say a circular region centered at the origin, or let us say a rectangle or a square and so on, how this function transforms certain regions of the plane into other regions of the plane on the other side. So, this geometrical point of view is often gives you sort of a better feel for what the function really does, and it sort of also leads naturally to notions of linear transformations and to matrices and various other connections to other things that we have talked about. So, but more on that next time.